Next, I'll discuss the main concepts behind projectile motion, and I'll use this example scenario to demonstrate the main ideas. This is the case of a car driving off of a cliff, and my students always like me to draw the guy driving the car. His name is Speedy, and he looks like this. He has to drive a convertible because he has this huge head, as you can see in the picture there. Now, Speedy's a cartoon character. He can do this without getting hurt, but you can't, so obviously you shouldn't be driving a car off of a cliff anywhere. But here he goes flying off of this cliff, and he starts off moving to the right. In this example, he starts off, his velocity, his initial velocity is horizontal, so he's leaving the cliff moving completely to the right, not up or down at all. But gravity pulls him down, and so he ends up heading down to the water in a path that looks something like that. Now, here are the main ideas. The velocity at any moment is tangent to the path. So if I say this is v0, maybe 1 second later I could call his velocity v1. It might look something like that. Or after 2 seconds we might have v2 that would look something like this, v2, and after 3 seconds v3 might look like this, v3. At any given moment, the velocity vector is tangent to the path. So the direction of the velocity changes as the path curves downward. The next thing I need to say is that the horizontal and vertical parts of the velocity have no effect on each other. And this is a general principle that applies to all two-dimensional motion. The horizontal and vertical motion can and should be considered independently. In other words, the fact that gravity pulls him down has no effect on his motion to the right, and the fact that he's moving to the right has no effect on the downward motion due to the pull of gravity. Next, I'll say this. The horizontal velocity is constant. If I draw in the components of these velocity vectors, v1 is to the right and down. So I could call this v1x and v1y, and v2 over here has components to the right. There's v2x and down, v2y, and then v3 here has a horizontal component, v3x, and a vertical component, v3y. If I've drawn this accurately, then the horizontal velocity is constant. That means v0 here is the same as v1x and v2x and v3x. All of those are the same. Gravity pulls him down, but gravity does not pull him forward or back. Gravity exerts no force to the left or to the right. So there's no acceleration in the horizontal direction. So the horizontal velocity doesn't change. The vertical velocity, though, is changing. And if this were drawn accurately, then there would be a steady increase in the length of these velocity vectors pointing down, the vertical components. Gravity pulls it down, so it accelerates down. There's an increase downward in the vertical component of the velocity. And then lastly, I'll say that mathematically, this path is a parabola. It's parabolic in shape. Now that's only true if there's no air resistance. In the real world, there is air resistance, which causes the shape to be a little bit different. But in the absence of air resistance, or at low speeds, when air resistance really is negligible, the path of the object is a parabola. Perhaps the most significant concept behind projectile motion is the fact that the horizontal and vertical components of the motion have no effect on each other. The horizontal motion and the vertical motion are completely independent, and they can and should be treated independently of each other. This fact leads to some surprising results in some situations. Let's consider this case. Suppose you're standing on the ground, and the ground is perfectly flat. And suppose you're standing here, and suppose you're holding a gun, and you fire a bullet out of the gun. So here comes the bullet. And you fire it perfectly horizontal. So there it goes flying out of the gun. And suppose at the same time you hold another bullet out here at the same height and you release it and let it fall straight down. So one bullet is falling straight down, accelerating down under the influence of gravity. The other bullet is flying over to the right. The one flying to the right, though, is also accelerating down under the influence of gravity. And it will go very far to the right. Bullets typically move very fast, hundreds of feet per second, or maybe even a couple of thousand feet per second. So it could go a long way to the right before it hits the ground. This diagram obviously wouldn't be to scale in this case. The point here is that the horizontal motion of the bullet, the fact that it's moving to the right, does not affect the vertical motion. It does not affect its downward fall. If we assume that the ground is perfectly flat and assume there's no air resistance, so there's no aerodynamic effects on the bullet at all, these two bullets will hit the ground at the same time. This one may fall and hit the ground in a very short amount of time. That the amount of time it takes this bullet to fall this distance will be the same amount of time that it takes the other bullet to fall that distance. The fact that it's moving to the right doesn't change its downward acceleration. It doesn't change the pull of gravity or the time it takes to reach the ground. If they start at the same height, this one is fired from the same initial height that that one is dropped, they will strike the ground at the same time. They both start off with a vertical velocity of 0, and they both are pulled down equally by the force of gravity. Now, if you aimed this bullet up initially, then obviously it would go way up before coming back down, and it would stay in the air much longer than the one that was dropped. Or if you aimed your gun down a little bit, then this bullet would have a very high, very large downward component, and it would hit the ground almost immediately and would hit the ground much sooner than the one that was dropped. But if they both start out with the same vertical velocity, in this case 0, they both end up hitting the ground at the same time. You can demonstrate this to yourself without a gun, just at lower speeds. If you have a table and a ball or some object, and you have someone stand over here beside the table. And this person holds an object right there. And then you stand over here. And you're going to give this object a shove, and it's going to go flying to the right, and when it gets to the edge of the table, it's going to start moving in a downward parabolic path like that. If right when it gets to the edge of the table, this other person releases this one and lets it fall straight down, then these two objects will be starting from the same position, and they'll both be starting with a vertical speed of 0. So one object leaves the table with a velocity to the right, and the other object is simply released at the same moment right beside it and allowed to fall straight down. And you'll see both of those hit the ground at the same time. And that will be the case regardless of the initial speed here. You could send this one flying really fast or just very slowly, but the horizontal speed won't affect the time that it takes to fall this vertical distance to the floor. And the one that is released with no horizontal velocity will fall at the same time. So they'll be moving downward. So you could see this like this. They both start at the same position, and then after this one has fallen a little bit, this one will be over here. And then when this one has fallen to this point, the one that was moving to the right would be about there. And they would both be at the same height above the ground at any given time, and they would both hit at the same time. And that's pretty easy just to demonstrate. Just have two people and a flat surface, and you can see that happen. The only tricky thing is that this person who's releasing the ball from rest needs to watch carefully and make sure he releases the ball right when the one moving horizontally gets to the edge of the table. If it's released a little bit early or a little bit late, they don't hit at the same time. But if the one dropped and allowed to fall straight down is released right when the moving ball gets to the edge of the table, you can see them hit the ground at the same time, regardless of the initial speed of the one moving horizontally.